Today, we're going to jump in the time machine and head back to 2018. Why? Because we're breaking down a paper that was honestly way ahead of its time. It laid out this super smart modular way to build AI systems, an idea that's more important now than ever before.
So here's our game plan. First, we'll tackle what I'm calling the monolith problem. Why just building one giant AI model isn't always the best move. Then we'll get into the paper's brilliant three-part solution. After that, we'll look at the secret sauce, this thing called a learnable bridge. We'll cover how you actually train a system like this, and we'll wrap it all up with the real-world benefits. All right, so let's set the stage. Back in 2018 and, even today, the default thinking was bigger is better. Just stack more and more layers on your AI model. But this paper came along and said, hang on a second, this is creating a whole new class of problems. And here's the core issue, the monolith problem. When you have one single, massive, sprawling network, it becomes a total beast to manage. I mean, if something breaks, where do you even start looking? It's like trying to find a single faulty wire in a skyscraper. These models get fragile, they cost a fortune to run, and they are an absolute nightmare from an engineering standpoint. So this really begs the question, doesn't it? Is just blindly adding more layers really our only option? Is that the only path forward? Or is there maybe a smarter, more elegant way to build powerful AI? Could we, break the problem down into smaller, more manageable pieces? And that question leads us directly to the heart of this paper. Its core proposal for a structured, three-part blueprint for designing AI. Okay, part one is the perception network. You should think of this as the system's eyes and ears. It's the part that takes in all the raw, messy data from the real world. An image, a chunk of text, whatever. And its only job is to boil it all down and pull out the most important features. So once you've got those clean features, you pass them to part two, the inference network. Now, if the first part was about seeing the world, this part is all about thinking. This is the brain of the operation. It's where the abstract reasoning happens, the planning, the heavy cognitive lifting. And finally, to complete the process, we have the generation network. This module takes the conclusions from the thinking part and turns them into something real, something concrete. It might spit out a sentence, tell a robot arm what to do, or even create a picture. This is the part of the system that actually does something. Okay, so having three separate networks is a cool idea, but it brings up a huge question. How do you connect them in a way that actually works? And this is where the paper gets really innovative, with a concept it calls the learnable bridge. Now, a learnable bridge is not just some passive pipeline for data. No way. It's an active, intelligent little module in its own right. It's a small, specialized network that sits between the big ones, and its entire purpose is to intelligently manage and control the flow of information passing through it. And to make this really robust, the bridge enforces something called a representation contract. Just think of it like a super strict API specification between two services. This contract defines everything, the exact shape and meaning of the data, rules to keep the connection from going haywire, what information gets through and what gets filtered out, and even a budget for things like latency and compute. It's an official agreement that keeps the whole system tidy and predictable. And what's really cool is that these bridges can be designed for different jobs. For example, a bottleneck bridge does exactly what it sounds like. It forces all the information through a tiny opening, squeezing out anything that isn't absolutely essential. Then you have something like a gated bridge, which is more like a series of smart valves that learn, over time, to only open for the most important features. Okay, this all sounds great in theory, right? But it raises a massive practical question. How in the world do you train a complex system made of three separate networks and two of these intelligent bridges all at once, without the whole thing just completely collapsing into chaos? Well, the paper proposes a super pragmatic, step-by-step approach. It's pretty clever. First, you just train the perception network all by itself. Once it's good, you freeze it, lock its weights in place, and then you train the next module and the bridge that connects to it. You do that again for the last stage. And only when every piece is kind of working on its own do you unfreeze everything for one final end-to-end fine-tuning session. It just adds so much stability to the process. Now, to make that stage training actually work in the real world, the paper points out a few engineering lifesavers. These are the crucial stabilizers. We're talking about things like putting normalization layers at every bridge to keep the data from getting weird, or using residual connections, which are like a guaranteed bypass lane for information, so the signal never gets completely lost. These are the little details that make the whole thing possible. So, that brings us to the big so what. Why would anyone go through all this trouble? What's the actual practical payoff for designing an AI system this way?
The benefits from an engineering perspective are just huge. First, debugging gets so much easier. If something's wrong, you can almost always isolate it to a single module. You get component reuse. You could swap in a brand new state-of-the-art vision module without having to retrain the whole reasoning system from scratch. It allows you to specialize. You can make your thinking module massive and complex without touching the other parts. It just gives you this incredible, predictable control over your system's cost and performance.
And look, the paper's author, Marcus Burgo, summed it all up perfectly. He called this modular architecture, and I quote, the engineering credible route to scalable capability. It's not just about building bigger AI. It's about building smarter, more reliable, and more maintainable AI.
And that leaves us with one last thought to chew on. Today, we have these enormous foundation models that are more powerful than anything we could have dreamed of back in 2018. So the question is, are they just bigger, more complicated monoliths? Or have they maybe quietly started learning the lessons from this forward-thinking blueprint? It's a question that really gets to the very heart of how we're building the future of intelligence.